Sodium and magnesium are next to each other on the periodic table, and we see their melting points. So sodium seems to be a lot less in melting point and a little less in boiling point. Which statement explains the differences in the melting and boiling point of these elements? Well, sodium and magnesium have different types of bonding. That's not true. Both of them are metals, so same reason. The electrostatic forces of attraction are stronger in magnesium. So the electrostatic forces are responsible for why something has a melting point or boiling point. The more the attraction, the harder it is to separate, so more heat is required to separate them. Essentially, that's what melting and boiling is. So let's rule out that they are different. Let's rule out that, well, actually this is correct, right? So that's our best bet, and actually it's correct. So it's not even our best, it's factual. The ionic bonds in magnesium are stronger than those in sodium. That might be true, but pure metals do not have ionic bonds. It's a metallic structure. The magnesium atoms are larger than the sodium atoms. That may be true. In fact, actually, it's not. Magnesium, coincidentally, funnily enough, is smaller than sodium. However, the atom are large, so like that has nothing to do with the attraction, so that gets ruled out. Our best answer right now is B. In which solid can layers of atoms slide over each other? Diamond is a giant covalent structure and there is no movement. Well, graphite it's also a giant covalent, but it has a special structure. So you know that graphite has these hexagonal sort of structure, and it's making these layers everywhere. So there are multiple layers, and these layers can slide on top of each other. Ta-da! And these layers can slide on top of each other, right? Because they have weak attraction between these layers. So that makes graphite our correct answer. Hematite, you probably haven't heard, is just iron oxide. That's a fancy name for it. Silica is sand, and that's also not the case. So silica and diamond have very similar structures. Graphite is the only exception to our 3 case studies that we do, which are for giant covalent structures, which are diamond, silica, and graphite. Diamond, sand, graphite. So our correct answer is B for today. This is an easy question, but a lot of people get this wrong. Which structure represents that of an alloy? What's an alloy? An alloy is simply a mixture of 2 different metals. Mixture. Right? So over here it doesn't look like a mixture because I don't see, it just looks like a metal, like a single metal. Over here again it looks like a single metal because it seems to be a molten version of A, because there seems to be randomly arranged, but I don't see any other ion. Over here I do see 2 different metals. This one's very tiny, so people might think it's a proton or something for some reason, but protons don't exist just willy-nilly. So this is our best bet, and our answer is C. What about D? Well, it's not electrons anymore. What are these negative things? Well, they're negative ions. So D is hinting at an ionic structure instead. That's ionic for you, or one version of it. So our best answer is C over here. The list shows some substances that conduct electricity. We have aqueous sodium chloride. Well, that's interesting because sodium chloride, that's an ionic compound. Copper, Cu, and graphite, which is carbon. So all of them are able to conduct electricity in their current state. So let's see what the question is. Which substances are only electrons responsible for the conduction or involved in the conduction? Well, over here there are no free moving electrons because the ions are free to move, and that's what allows the conduction for ionic compounds. Whereas for copper and carbon, graphite, the only non-metal that can conduct electricity, it is free moving electrons. So our best bet is B. Yay. A metal consists of a lattice of positive ions and a sea of electrons. What happens to the electrons and positive ions in a metal wire when an electric current is passed through it? The electrons are replaced by new electrons, right? And that very much makes sense to quite a few people, I believe. So that's true, and this is true. But what about positive ions? The positive ions actually don't move. So let's mark the correct version of that, unchanged and unchanged. So B, that's our answer. In the ionic solid zinc phosphide Zn3P2, what is the formula of the phosphide ion? Well, some basics. This is a good question where a lot of people can just come up with ionic formula for ionic compounds, but this really tests your understanding, right? So let's take a look at zinc and then take a look at phosphorus. So zinc could have a +1 charge, right? And there are three zincs. So a total charge contributed by these three zincs will be, well, +3, right? So there are only two phosphorus over here, and the charge on the phosphorus will be some negative. So I'll never get enough phosphorus. Like, let's say the charge on phosphorus is -1. So if I have one negative phosphorus, I can only have two negative phosphorus, so the total charge will be contributed over here as -2. These two charges aren't balanced, so these aren't the correct charges, right? So what's the best? So let's change the charge on zinc now. So now let's assume that the charge on zinc is 2+, because +1 isn't working out. If it's +2, because of the three zincs, is going to go up to +6. And you want -6 over here. And you can only multiply this number, whatever this is, this number, by 2, because there are only two phosphorus. So what could this number be? Well, this number has to be, well, it has to be 3. +3. Because +3 times 2, sorry, -3. This has to be a -3. So if it's a -3 times 2, because there are only two, 6. Now it's pretty balanced, right? So out of all the options, your best bet is, well, A. The table gives the melting points, densities, and electrical conductivities of 4 elements. Which element is copper? So copper will generally have a high melting point because it's, at one point, copper was popular to make pots and pans out of for cooking utensils, because it was very good. Even in metals, it was probably the best to conduct electricity and heat. Heat's the important factor here, right? So all of these melting points are not good for cooking utensils. Why? Well, this is already a liquid at room temperature because it melts at -38. So at room temperature, it's probably a liquid or gas even, right? One of the two. Same with B. C could be a possibility, but before you can boil water in this thing, it'll melt because it melts at 97. So bad cooking utensil. You're already left with the only answer, which is D. And let's just confirm, copper's pretty heavy, so density is much heavier. And, well, this doesn't really help. Most of them are good anyway. So, yeah, D is our answer. Which diagram best represents the structure of a solid metal? Well, solid, right? So A doesn't look like a solid, and there are no electrons over here. These are negative ions. So that's ionic. So let's highlight that. We are talking about ionic. For B, that looks a lot like a metal. What's wrong with B? But the problem with B is, I think it's a molten metal because the ions aren't arranged neatly. What's wrong with C? C is perfect. D is just weird. The diagram shows electrons are all around it. So D is out, so best answer is C.